Good morning, dear students. Welcome back to physics class. Today, I would like to discuss on the topic significant figures part B. For today's class, I present the role of significant figures in measurement in more details. In last class session, you had studied the basic nature of significant figures. You have to note that the result of a calculation involving approximate measured values of quantities, that is, values with limited number of significant figures, must reflect the uncertainties in the original measured values. It cannot be more accurate than the original measured values themselves on which the result is based. In general, the final result should not have more significant figures than the original data from which it was obtained. Suppose, if mass of an object is measured to be 4.237 gram, here this number has the 4 significant figures and its volume is measured to be 2.51 centimeter cube. Then density can be calculated by using this formula, mass divided by volume, which will be equal to 1.6880478086 gram per centimeter cube up to 11 decimal places. So, it would be clearly inappropriate and irrelevant to record the calculated value of density to such a precision when the measurements on which the value is based have much less precision. So, we have to follow certain rules for arithmetic operations with significant figures. Now, you are going to study about these rules which are used for the arithmetic operations with significant figures. These rules ensure that the final result of a calculation is shown with the precision that is consistent with the precision of the input measured values. The two important rules are: first one, multiplication or division, the final result should retain as many significant figures as are there in the original number with the least significant figures. And second one is, in addition or subtraction, the final result should retain as many decimal places as are there in the number with the least decimal places. This table shows the way of usage of the rules appropriately. Rule number 1, which is used for multiplication or division. The final result should retain as many significant figures as there in the original number with the lowest number of significant figures. Let us consider this example. Suppose mass of an object is 4.237 gram, its value with the 4 significant figures, and the object's volume is 2.51 centimeter cube. This value has 3 significant figures. Then what should be the density of this object? By using the formula, density is equal to mass divided by volume. By the calculation, it will giving to 1.68804 gram per centimeter cube. By using the rule given, it can be round off to 1.69 gram per centimeter cube. Here, this value has 3 significant figures because the result should have the same number of significant figures that's seen in the quantity volume 2.51 centimeter cube, which is having lower number of significant figures, that is 3. And rule number 2 says the final result should retain as many decimal places as there in the original number with the least decimal places. For example, suppose you are going to add 3 numbers. The numbers are 436.32, 227.2 and 0.301. First number has 2 digits after decimal, that is, it has 2 number of decimal places. Second number has 1 digit after decimal place, that is, it has number of decimal place is equal to 1. And third one has 3 digits after decimal, that is, it will have 3 number of decimal places. When these numbers are added, you will get 663.821, which is having 3 number of decimal places. Since 227.2 is precise up to only 1 decimal place, that is, it has 1 number of decimal place, so the final result should be rounded off to 663.8. As the final result should have the same number of decimal places as seen in the number 227.2, which is having 1 number of decimal place. This is the way by which the rule is employed. On next, you are going to study about how to round off the uncertain digits. It is very important to round off the result of computation with approximate numbers which contain more than 1 uncertain digit. Here, I have categorized the situations or conditions into 3 ways, where 3 different rules are applied. First one, the rule by convention is that the preceding digit is raised by 1 if the insignificant digit to be dropped is more than 5. What is the meaning of the preceding digit? It is the digit just before. Consider a number 9.728, which can be rounded off to 3 significant figures, that is 9.73. In this case, insignificant digit, which is underlined already in this number, it is 8 and the preceding digit is 2. Here, 8 is the insignificant digit which is to be dropped greater than 5, so the preceding digit 2 should be raised by 1 to get 3. So the final number will be 9.73. And the second rule is the preceding digit in a number is left unchanged if the insignificant digit to be dropped is less than 5. For this, I give one example. The number you have to consider is 5.973. According to this rule, it can be rounded off to 5.97 because 3 is the insignificant digit which is lower than 5. Therefore, the preceding digit should remain unchanged and the number should be rounded off to 5.97 by the removal of the insignificant digit 3. And the third rule shows its application in 2 different cases. First case, when a number whose preceding digit is odd is concerned, the preceding digit is raised by 1 if the insignificant digit to be dropped is 5. For example, Consider a number 1.7535, which can be rounded off to 4 significant figured number, that is 1.754. Here, insignificant digit is 5, which is already underlined, and its preceding digit is 3, which is odd number. So, it should be rounded off to 1.754 when the preceding digit 3 is raised by 1. And the second case shows that if the preceding digit is even, the insignificant digit is simply dropped. For the clarity of the subject in second case, consider the number 2.785. By this rule, the number 2.785 should be rounded off to 3 significant figured number, which is 2.78, since the preceding digit is even number. Now, I am going to discuss on this subject how can round off the uncertain digits in some special cases. In any involved or complex multi-step calculation, you should retain in intermediate steps one digit more than the significant digits and round off to proper significant figures at the end of the calculation. Similarly, a number known to be within many significant figures, such as in 2.99792458 into 10 to the power of 8 meter per second for the speed of light in vacuum is rounded off to an approximate value, that is 3 into 10 to the power of 8 meter per second, which is often employable in common computations. It needs to notice that exact numbers that appear in formulae like 2 pi in t is equal to 2 pi root of L by G have a large or infinite number of significant figures. Why does it happen? Because the value of pi is equal to 3.1415926, which is going to substitute in the expression t is equal to 2 pi root of L by G. This is the formula used to calculate the time period of a simple pendulum, which is known to a large number of significant figures. So you can take the value as 3.142 or 3.14 for pi with limited number of significant figures. Next topic is rules for determining the uncertainty in the results of arithmetic calculations. To calculate the uncertainty, below process should be used. Step 1. Add a lowest amount of uncertainty in the original numbers. For example, uncertainty for the number 3.2 will be plus or minus 0.1, and for 3.22 it will be plus or minus 0.01. It should calculate the percentages of their uncertainties. How can calculate the percentage of uncertainty? For example, the percentage of 0.1 in 3.2 is equal to 0.1 divided by 3.2 into 100. Step 2 is, after the calculations, the uncertainties get multiplied or divided or added or subtracted. And step 3 is, round off the decimal place in the uncertainty to get the final uncertainty result. Example, for a rectangle, if length L is equal to 16.2 centimeter and breadth B is equal to 10.1 centimeter. Then take L is equal to 16.2 plus or minus 0.1 centimeter or 16.2 centimeter plus or minus 0.6% and breadth B is equal to 10.1 plus or minus 0.1 centimeter or 10.1 centimeter plus or minus 1%. By multiplying length and breadth, we get area which is equal to 163.62 centimeter square plus or minus 1.6% or 163.62 plus or minus 2.6 centimeter square. Why does add the percentage arrays here? See the rule used in combinations of arrays, which you have studied in your previous class. As Z is equal to A into B, then delta Z by Z is equal to delta A by A plus delta B by B. They are the relative arrays. Or delta Z by Z into 100 is equal to delta A by A into 100 plus delta B by B into 100 when the relative arrays are expressed in their percentage. Therefore, after rounding off, area is equal to 164 plus or minus 3 centimeter square. Hence, 3 centimeter square is the uncertainty or the error in the estimation. On next part, let me see how do the rules use in special cases. First case, for a set experimental data of n significant figures, the result will be valid to n significant figures or less only in case of subtraction. For example, 12.9 minus 7.06 is equal to 5.84, which has rounded off to 5.8, whereby rounding off is done to lowest number of decimal places of the original number. Second case is the relative error of a value of number specified to n significant figures depends not only on n but also on the number itself. For example, accuracy for two numbers 1.02 and 9.89 are plus or minus 0.1, but their relative errors will be for 1.02 it is plus or minus 0.1 divided by 1.02, and for 9.89 plus or minus 0.1 divided by 9.89. Their respective percentage errors are plus or minus 0.01 divided by 1.02 into 100% is equal to plus or minus 1%, and plus or minus 0.01 divided by 9.89 into 100% is equal to plus or minus 0.1%. Here you have seen that the relative arrays or the percentage arrays are the two different. Thus, the relative error depends upon number itself. And third case is intermediate results in multi-step computation should be calculated to one more significant figure in every measurement than the number of digits in the least precise measurement. For example, if you are going to take reciprocal of 9.58, you will get 0.1044, whose reciprocal should be equal to 9.58. But if you are going to take the reciprocal of 0.104, it will be equal to 9.56, not 9.58. See the difference? So we have to accept 0.1044 instead of 0.104. This example justifies the idea to retain one more extra digit in intermediate steps of the complex multi-step calculations in order to avoid additional errors in the process of rounding of the numbers. In last session, let me discuss on numerical. First question is the length, breadth and thickness of a rectangular sheet of metal are 4.234 meter, 1.005 meter and 2.01 centimeter respectively. Give the area and volume of the sheet to correct significant figures. Let you see the solution. Given that length of sheet L is equal to 4.234 meter, breadth B is equal to 1.005 meter and its thickness H is equal to 2.01 centimeter, which is converted into meter. It will be equal to 0.0201 meter. By the rule used in these arithmetic operations, area and volume both must have least significant figures, that is 3, which can be noted from the table given above. Then surface area of the sheet is equal to 2 into L into B plus B into H plus H into L, which is equal to 8.72 meter square. Can you say how many significant figures are there in this number? It has 3 significant figures. By applying the same rule, you can find the volume of the sheet, which is equal to 0.0855 meter cube. The number of significant figures in this result is also 3. And second question is the mass of a box measured by a grocer's balance is 2.300 kilogram. 2 gold pieces of masses 20.15 gram and 20.17 gram are added to the box. What is A, the total mass of the box, and B, the difference in the masses of the pieces to correct significant figures? What should be its solution? Given that mass of the grocer's box is equal to 2.300 kilogram, mass of gold piece 1 is equal to 20.15 gram. When it converted into kilogram, it is equal to 0.02015 kilogram, and mass of gold piece 2 is equal to 20.17 gram, which is equal to 0.02017 kilogram. Then total mass of the box is equal to 2.34032 kilogram. The value of the total mass of the box can be rounded off to 2.3 kg by using the rule which says that in addition, the final result should retain as many decimal places as there are in the number with least decimal places. Hence, the total mass of the box should be equal to 2.3 kg. On next, you have to find the difference in masses of the 2 gold pieces. It will be equal to 0.00002 kg. It has 5 decimal places, followed by the rule which says that In subtraction, the final result should return as many decimal places as there are in the number with the least decimal places. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.